Swayam Prabha. Digital India. Educated India.
Now, next topic is continuous optimization. Since machine learning algorithms are implemented on a computer, the mathematical formulation are expressed as a numerical optimization methods, and this topic describes the basic numerical methods for training machine learning models. Training a machine learning model often boils down to finding a good set of parameters. The notion of good is determined by the objective function or probabilistic model. So, the flowchart describe about that the concept of optimization in the area of different areas, like start from the objective function and descriptive function, you have to take it, and that function is a continuous optimization. It may be a constraint optimization or unconstrained optimization. So, constraint is based on the variable what we are taking, and unconstrained you have to take sometimes gradient descent is going to the unconstrained, whereas constraint optimization deals about the Lagrange's multipliers, and Lagrange's multiplier we have to take it into account and then check it out whether it is convex or convex optimization and duality is working or not. If it is convex optimization, then convex conjugate you have to check it out, and once you got that Lagrange's multiplier, then the equation is converted to linear programming problem, and we have a lot of LPP method to find out the optimization of the technique. Now, once you know optimization of the convex, then quadratic programming you have to convert. Based on that, lot of classification we can do. Suppose the problem is unconstrained, the gradient descent check you have to do for, and use the step size technique, apply it, as well as momentum also check it out. So, the gradient descent actually based on the stochastic gradient descent. So, these are all the other area of unconstrained optimization will come, whereas a constraint optimization further reduced to dimensional reduction and density estimation. So, these are all the subdivisions of any objective function subject to the constraint, and optimize the technique of the given function, whether it is a feasible or infeasible, bounded or unbounded, and it has a no solution or not. These are all the things we have to check it out, and these can be easily mapped the related to optimization ideas, and our focus is to do for the gradient descent and convex optimization. That is the meaning of flowchart. Now, consider the function, this one is objective function, and this is the equation L of x equal to x power 4 plus 7x cube plus 5x square minus 17x plus 3, and this function has a global minimum around x equal to minus 0.45 with the function value approximately minus 47. The function is smooth. The gradient can be used to help finding the minimum by indicating whether we should take a step to the right or left. This assumes that we are in the correct bound, as there exists another local minimum around x equal to 0.7. And recall that we can solve for the stationary point function by calculating its derivatives and setting to 0. So, L of x you take it x power 4 plus 7x cube plus 5x square minus 17x plus 3 is biquadratic, and if you differentiate with respect to x power 4 differentiation is 4x cube, 7x square is differentiation 7 into 3 into x square, it becomes 21x square, 5x square differentiation is 10x, minus 17x is differentiation minus 17. So, after derivative the equation 7.2 represent the cubic equation. It has in general 3 solution because it is a cubic equation. When set to 0 and 2 of them are minimum and 1 is maximum, whether the point is a stationary point in a minimum or maximum. So, we need to take the derivative a second time and check whether the second derivative is positive or negative. If it is negative, the second derivative, then the function is maximum. If the second derivative is positive, then function is minimum at the stationary point. So, in our case the second derivative is d square Lx by dx square is equal to 12x square plus 42x plus 10. After substituting the value of x equal to minus 4.5, minus 1.4 and 0.7, the point got because of this equal to 0. So, that the 3 values will come. Based on these 3 values, we have to substitute in the second 7.3, and if second derivative is negative, the function is maximum and other 2 stationary points or minimum will come. So, where the point the blue dot represent, right, the corresponding values of where the maxima and minima, and we can easily plot through the graph. So, we can find the global maximum and global minimum with the help of the graph. We can easily identify it. Based on the feasibility we can check. So, note that we have avoided analytically solving for values of x in the previous discussion. For low order polynomials such as the preceding we could do. In general, we are unable to find analytical solution because it is not easily finding the solution to the problem. Therefore, we start some value, say x naught equal to minus 6 and the follow a negative gradient. So, this negative gradient indicates we should go right, but not how far it is so called the step size. So, if we had started the right side, the negative gradient would have to lead to the wrong minimum. So, from the figure, this is a 7.2 figure, illustrate the fact that for x is greater than or equal to minus 1. So, the negative gradient point towards the minimum on the right of the figure, which have a larger objective values. So, these are things we can easily understand from the picture how the gradient is indicate and so on. Now, keep it in mind, let us go with optimization using gradient descent. The problem solving for minimum real valued function, minimum of f of x subject to the x, where f such that r power d to r mean r d tuple to r is objective function that capture the machine learning problem at hand, and assuming our function is a differentiable. I hope all of you know about it, and we are unable to analytically find the solution to closed form. So, the gradient descent is a first order optimization algorithm to find a local minimum of a function using gradient descent. One takes steps proportional to the negative of the gradient of the function at the current point. So, let us consider the multivariate function. Imagine a surface, describe the function f of x with a ball starting at a particular location x naught. When the ball is released, it will move downhill in the direction of a steepest descent. and the gradient descent exploits the fact that f of x naught decreases, and the fastest if one moves from x naught in the direction of the negative gradient, that is minus of delta f of x naught of f at x naught. So, we assume this talk that the function are differentiable, and one may refer to more general setting of this, the following section. If x1 equal to x naught minus nu into del f of x naught into t, del f is a gradient of f of x naught into whole power transpose. So, for nu is positive and f of x1 less than or equal to f of x naught. So, we use the transpose of the gradient, otherwise dimension will not work out. Now, from this observation, we define a simple gradient descent algorithm of n tuple to R, that is, you take x value and corresponding f of x, then by iteration process of finding the optimization of x suffix I plus 1 equal to xi minus nu I into gradient f of xi whole power transpose. So, this is suitable for size nu I of the sequence of what the decreasing f of x naught, f of x1 and so on, and converges to a local minimum. So, this is the theory. We have to understand how the iteration process is working. Now, let us demonstrate one example. If you take the quadratic function in 2-dimensional x1, x2, that can be written as x1, x2 transpose. So, the equation comes like that, that is x1, x2 into 2, 1, 1, 20 equal to x1, x2. This is called as quadratic expression, quadratic form this is. So, it becomes 2x1 square plus 20x2 square will come, because multiply with the second matrix and third is 2x1 plus x2, and third one is x1 plus 20x2, and then multiply with this one, it becomes 2x1 square plus x2 square will come, and subtract with 5x1 minus 3x2. So, everything can be right in terms of the matrices, so that the problem is easily solvable. So, we have to check it out the gradient. The technique is del of f of x1, x2. It means you take x1, x2 transpose of the matrix minus this one, that is called it as del f, because del f is dou by dou x1 plus dou by dou f x2, and differentiate it and simplify, you get this one. And then after solving this equation 7.8, we have the values of x naught equal to minus 3, minus 1 is a solution to the problem. Now, you take 7.6 and substitute I equal to 1, 2, 3 and so on, because x naught you got it, and then substitute in the equation of 7.6, you can get infinitely many solution, will get iteratively. After getting all the values and substitute in the x axis, y axis with the help of the map, that is Maple or MATLAB, you have to use it. So, the figure plugging x naught into 7.8 with the nu equal to 0.08, it means the negative gradient at x naught point is leads to the next point will come minus 1.98, 1.21. Now, repeating the argument x1, x0, x2, x and so on, and now you have to plot on the graph, and it goes like this, the map. See, the yellow waves represent the point actually converges the one point. So, that point is required. This is called it as gradient search method of the optimization. So, this is most wanted in machine learning and AI. So, this is the 2-dimensional quadratic surface for a convergent description. So, we have a note, a gradient descent can be relatively slow close to the minimum. Its asymptotic rate of convergence is inferior to many other methods. Using the ball rolling down the hill analogy, when the surface is long, thin valley, the problem is poorly conditioned, and for poorly conditioned convex problems, gradient descent is increasingly zigzag. So, this is a zigzagly will come. As the gradient point nearly orthogonally to the shortest direction to the minimum point, and the figure 7.3 shows like that. So, this is the picture that demonstrated in the note, and these are all the initial technique to finding the gradient search. Next, we have to understand step size. So, earlier we mentioned choosing a good step size is important. If the step size is too small, the gradient descent can be slow. If the step size is chosen too large, the gradient descent can be overshoot and fail to converge or even diverge. So, that is the difference between the choosing of the step size is a minimum or greater, or minimum or small or large. So, based on the choosing of the step size, according to the consequence of the solution will come. So, now we will discuss the use of momentum in the text. When the function value increases after a gradient step, the step size was too large, undo the step and decrease the step size. When the function value decreases, the steps would have been larger, and this try to increase the step size. Now, we have an example solving a linear equation system. When we solve the linear equation of the form Ax equal to b in practice, so we can write Ax equal to b is Ax minus b equal to 0 approximately. So, finding x. So, the minimized squared error is a norm of Ax minus b square is equal to Ax minus b whole transpose into Ax minus b. So, it is called as a Euclidean norm, that also we discussed in the earlier chapter. Now, the gradient of 7.9 with respect to x is nothing but del x is gradient of x, which is equal to twice of, this is simply do the difference twice of Ax minus b into A. So, this gradient directly in the gradient descent algorithm. Next note. So, when we apply the solution of the linear system of equation Ax equal to b, so the gradient descent may converge slowly. So, the speed of convergence of gradient is k equal to sigma of A by sigma of A, with the numerator is maximum, denominator is minimum is a condition. So, based on this condition, which you have to check it out, the is a singular value or not. So, the ratio of minimum or minimum maximum to minimum is a singular value of A. So, the condition number essentially measures the ratio of the most curved direction versus the least curved direction, which correspond to our imaginary that poorly conditioned problems are long, thin valleys. So, they are very curved in one direction, but very flat in the other. Therefore, if you directly solve Ax equal to b and solve P inverse of Ax minus b equal to 0, then P is called as preconditioner. So, the goal is designed to P inverse such that you multiply that P inverse A had a better condition number, but at the same time P inverse is easy to compute. So, we have a further information on the gradient descent, and precondition and convergence we refer the Boyd and Vanderberg in the theory they develop in the chapter. Now, we have a gradient descent with the momentum. So, gradient descent with momentum is a method of introduce the additional term to remember what happened in the previous iteration. So, the memory dampens the oscillation and smoothness out of gradient updates. So, continuing the ball analogy, the momentum terminates the phenomena of the heavy ball that reluctant to the change of the direction, and the gradient update the memory to implement. So, the momentum based method remembers the update of delta xi at the each iteration I and determines the next update as a linear combination of the current and previous gradients. So, based on the previous ideas delta xi plus 1 equal to xi minus nu I into delta f of xi the whole transpose plus alpha delta xi. From this delta xi equal to xi minus 1, this is a step size of one step to the back step, and substitute xi from the previous one, we have alpha into delta xi minus 1 minus nu I minus 1 into delta f of xi minus 1 the whole transpose. So, here alpha lies between 0 to 1. Sometimes we will only know the gradient approximation, and the momentum term is useful since it averages out different noisy estimates of the gradient. So, one particularly useful way to find the system is minimum of the descent. Next, we have a stochastic gradient descent. So, it is often called it as GD of for minimizing the objective function with written as a sum of differential function, that is the meaning of stochastic gradient descent. The word stochastic refers that the gradient precisely, but instead only a noisy approximation to it. So, by constraining the probability distribution of the approximation gradient, the stochastic gradient guarantee that it will converge the ideas. So, that is the most of them are applying the stochastic ideas. So, in machine learning, you take the value n equal to 1 to n data points, and we often consider the objective function that are sum of losses L n incurred by each example n. So, in mathematical notation we have L of theta equal to summation n equal to 1 to n ln of theta, where theta is a vector of parameters of interest. So, in this we have to find the theta for minimum L, and also next idea we have to discuss the regression. There we can use the negative likelihood, which is expressed as sum of over likelihood of the individual. For examples, L of theta equal to minus summation n equal to 1 to infinity log of p of yn over xn comma theta, probability of this one. So, xn equal to r power d are training inputs, yn are the training targets, and theta are the parameter of the regression model. So, keep it in mind these ideas, and then we will go to the stochastic gradient descent. Now, we have a standard gradient descent, and previously we have to discuss the optimization of this. Optimization means maximum of minimum equal to minimum of maximum. So, here we are applying the optimize is performed using full training set by updating the vector parameters according to the iteration process of theta. So, theta varies from I to I plus 1 equal to theta I minus nu I into delta L theta I whole transpose equal to what? Theta I minus nu I into summation n equal to 1 to n delta ln theta I of whole transpose. So, this formula we have to use for using the standard gradient descent, and we have to choose the suitable step size corresponding the parameter nu I. Therefore, some gradient may require expensive evaluation of gradient from all individual functions. Therefore, the training set is enormous and no simple formulas exist. Now, we have to sum the gradient and it becomes very expensive. Now consider summation n equal to 1 to n delta ln of theta I. So, we can reduce the amount of the computation by taking sum over the smallest set of ln. In contrast to batch gradient descent, so we randomly choose the subset ln for mini batch gradient. So, in the extreme case, we randomly select only a single ln to estimate the gradient. So, the key insight about why taking a subset of data is sensible to realize for the gradient descent to the converge. We only require that the gradient is an unbiased estimate of the true gradient. So, in fact, the term summation n equal to 1 to n of a delta of ln of theta I is an empirical estimate of the expected value of the gradient. Therefore, any unbiased empirical estimate of the expected value, we have an example using a subsample of the data would suffice the converge of the gradient descent. So, note, when the learning rate decreases at an appropriate rate subject to the relatively mild assumption, stochastic gradient descent converges almost surely on to local minimum. So, that is an important note we have to make with the help of stochastic gradient descent corresponding to gradient descent, where it is converges, where it is a minimum, where it is a local minimum and so on, we can easily calculate. Now, these are all the topics belongs to the constraint optimization technique. One is called it as a direct method, another one is indirect method. In direct method, these are all the subdivisions. Number 1, random search method. Number 2, heuristic search method, and also complex method included. Objective and constraint approximation method, sequential linear programming method, sequential quadratic programming method, method of feasible direction, Zotansik's methods, Rosen gradient methods and generalized reduced gradient method. These are all direct method. Whereas the indirect method consists of what? 3 ideas, 3 associated with 4. So, transformation of variable technique, sequential unconstrained minimization technique, interior penalty function method and exterior penalty function method, and these associated with augmented Lagrange's multiplier method. So, these are all the methods to attack the problem related to constraint optimization technique. Let us go with one example. The constraint may have no effect on the minimum point, that is, the constraint minimum is same as the unconstrained minimum as shown in the figure 7.1. In this case, the minimum point x star can be found making the necessary and sufficient condition of delta f of x with respect to the x star is 0 and j x star equal to dou square f by dou xi into dou xj of x star, and check it out, this value of the second order partial differential equation at x star is a positive definite, then we can move to further. Here the figure represent the constraint and unconstrained minima same. So, using the GD, that is gradients descent method of searching the gradient descent method, and the value is converges, and check it out where the optimum. So, f optimum equal to 0, f then x of optimum is 1 comma 2, this point is converges, and we have to make a gradient search related to the equation. So, the equation comes 4 minus x1 minus x2 equal to 0, and if you solve them, we have the function value f, and f having that 0.0625 converges from f 0.5 to 0.06. So, where the point is converges we can easily identify. Now, this is the topography of what we have taken the convergence of the nonlinear constraint. So, constraint minimum occurring in on the nonlinear constraint with the help of the minus delta f equal to lambda delta gi. So, it converges from which point to which point we can easily identify. Based on that, where the optimization comes also identified. So, this point is optimized with what minimum of maximum equal to maximum of minimum occurred. So, that is the most converges point at this point. And this is a relative minima and introduced by the objective function, that is objective with respect to the constraint, and then we got that maximum optimum at that point B, and at one first iteration and second we have at B. So, the f started from 19 and then go to the sequential pattern 19, 11 and so on. So, this way we have to search the gradient search, find out the solution to the problem. Now, it is used this condition. However, to use the condition, one must be certain that constraints are not going to have any effect on the minimum. For simple optimized problem like the one shown in the figure, it may be possible to determine beforehand whether or not the constraint have an influence on the minimum point. However, in the most practical problems, even if you have a situation as shown in the figure, it will be extremely difficult to identify it. Thus, one has to proceed with the general assumption that the constraint has some influence on the optimum point. So, the optimum point is unique solution occurs on the constraint boundary as shown in the figure. In this case, we have to apply Kuntakar necessary condition, indicate that negative of the gradient must be expressible as a positive linear combination of the gradient of the active constraints. If the objective function has a 2 or more unconstrained, then local minima, the constraint problem may have a multiple minima as shown in the figure. In some cases, even if the objective function has a single unconstrained is a minimum, then constraint may be introduced multiple local minima as shown in the figure 7.4. So, the constraint optimization technique must be able to locate the minimum in all the situations outlined above. So, this is the picture shows the relatively minimum introduced by the constraint F1, F2, F3 and so on. Now, we have to go to the next idea is called it as a random search method. The random search method is described for unconstrained minimization, can be used with a minor modification to solve a constraint optimization problem. So, that is our goal to go to the random search. Now, we have a procedure number 1, generate trial design vector using one random number for each design variable. This is the first point. Number 2, verify whether the constraints are satisfied at the trial design vectors. Usually, the equality constraints are considered satisfied whenever their magnitude lie within the specified tolerance. If any constraint is violated, continue generating new trial vectors until a trial vector that satisfies all the constraints is found. 3. If all the constraints are satisfied, retain the current trial vector as the best design if it gives a reduced objective function value compared to the previous best available design. Otherwise, discard the current feasible trial vector and proceed to step 1 to generate a new trial design vector. 4th, the best design available at the end of the generating a specified maximum number of trial design vectors is taken as the solution of the constraint optimization problem. So, it can be seen that several modifications can be made to the basic procedure indicated above. For example, after finding feasible trial design vector, a feasible direction can be generated, and one dimensional search can be conducted along the feasible direction to find an improved feasible design vector. So, another procedure involves constructing unconstrained function f of x by adding a penalty for violating any constraint as described. So, we have capital F of x equal to small f of x plus a into summation j equal to 1 to m gj of x square plus b into summation k equal to 1 to p hk of x square, where gj of x square is maximum of 0 comma gj of x whole square. So, hk of x whole square is hk x square. So, this indicates the square of the violation of the inequalities and equality constraint, respectively a and b are constant, and the equation 7.4 indicates that while minimizing the objective function f of x, a positive penalty is added whenever a constraint is violated. So, the penalty being proportional to the square of the amount of the violation. So, the values of the constant a and b can be adjusted to change the constraint of the penalty terms relatively to the magnitude of the objective function. So, we have to note random search method are not efficient compared to other method described in the chapter. However, they are very simple to program and usually reliable in finding nearly optimization solution with a sufficient large number of trial vectors. So, this method can find near global optimal solution, even the feasible region is non-convex. So, the last paragraph is most important, and which one is important, which one is not important described in the last paragraph. Now, we are going to discuss the sequential linear programming. So, this anacron SLP stands for sequential linear program, right, the acronym corresponding to this. So, can be stated as follows: start with the initial point x1 and the set of iteration number as I equal to 1, then the x1 need not be a feasible. Number 2, linear is the objective constraint function about the point xi as f of x equal to approximately equal to f of xi plus delta of f of xi whole transpose of x minus xi, and gj of x is approximately gj of xi plus delta gj of xi transpose into x minus xi. H of x equal to approximately equal to h of k of xi plus delta hk of xi transpose into x minus xi. So, based on these three and formulate the approximating linear programming problem as minimization of f of xi plus delta fi lambda of x minus xi subject to the constraint gj of xi plus delta gj of xi transpose into x minus xi is negative, and hk of xi plus delta hk of xi transpose into x minus xi equal to 0. So, these are all the 2 points are subject to the constraint of the objective function of f of x. So, keep it in mind this way we have to formulate. And fourth point, solve the approximating LP problem to obtain the solution vector x suffix I plus 1. Evaluate the original constraint at x I suffix plus 1, that is finding gj of x suffix I plus 1 is j varies from 1 to m, and hk of xi plus 1 where k varies from 1 to p. If gj of xi plus 1 is less than or equal to epsilon for j equal to 1 to 3 and so on m, then the modulus of hk of xi plus 1 less than or equal to epsilon where k varies from 1 to p. If epsilon is a very small positive tolerance, so all the original constraint can be assumed to have been satisfied, Now, hence stop the procedure by taking x optimum equal to approximately equal to xi plus 1. If x optimum is approximately xi plus 1, then g of xj, gj of xi plus 1 is always greater than epsilon for all some j, or modulus of hk of xi plus 1 is greater than epsilon for some k. Now, find the most violated constraint, for example, as gk of x suffix I plus 1 equal to maximum of gj of x suffix I plus 1, and relinearizing the constraint gk of x is negative about the point x suffix I plus 1. So, gk of x equal to approximately gk of xi plus 1 plus delta gk of xi plus 1 transpose into x minus xi plus 1 is negative. Now, add this as m plus 1th inequality constraint to the previous LPP problem. Therefore, the new iteration number I equal to I plus 1 will come. So, the total number of constraints in the new approximation linear programming problem as m plus 1 inequalities and p equalities. Then go to step 4, and then step 4 solving the LP problem to obtain the solution to the vector, and proceeding in this way we can get the optimum solution to the problem. So, the sequential linear programming has several advantages. It is an efficient technique for solving complex convex programming problem, nearly linear objective and constraint functions. And next advantage is the problem will be LP problem and hence can be solved quite efficiently. Moreover, any two consecutive approximating LP problem is differ by only one constraint, and hence dual simplex method can be solved by sequential approximation in LP problem more efficient. So, the method can easily be extended to solve the integer programming problem. In this case, one integer LP problem has to be solved in each stage. Next, we have to discuss about the geometric interpretation of method. In SLP method can be illustrated with the help of the one variable problem. Minimize f of x equal to c1 x subject to the constraint g of x is negative, where c1 is a constant, g of x is a nonlinear function. Then it is a feasible region and contour of the objective function is shown in the following figure. This is figure 7.5, where the minimization of f of x equal to c1 x is demonstrated. If g of x subject to the constraint is described, then and where x lies between c to d, then we have to have the equation having the decrease f as well as f of x equal to c1 of x, got it. Using that g of x is equal to 0 or negative or positive. Based on this algorithm, we can demonstrate the picture like this. Now, we have to take the constraint when x is lies between c to d, where c and d represent lower and upper bounds of the x. So, that we have the formulator of LP problem is like this. So, outside the feasible region and converge towards a true optimum point x equal to a. So, the process is assumed to have converge whenever the solution of an approximate problem satisfy the original constraint within some specified tolerance level of g of xk star is less than or equal to epsilon, where epsilon is small positive integer and xk star is a optimum solution of the kth approximation LP problem. So, it can be seen that the line hyperplanes defined in g of xk star plus dg by dx of xk star of x minus xk star. So, cut off the portion of the existing feasible region, hence this method is called it as cutting plane method.